Okay, we're going to move into our final measure of spread. We've looked at range, we've looked at IQR. Today we're going to be looking at variance and standard deviation. So, what do we have here? So, standard deviation, it's probably considered more powerful measure of spread than IQR. Mainly because it takes into account how far each data value is from the mean. Actually, if you want a good sort of quick definition for standard deviation, it's the average of the spread each data value has from the mean of the data set. So it's an overall kind of snapshot of how far away from the mean a typical data point is. Some are farther away, some are closer, but it's an overall average. But it's a little bit more complicated than that. Now, a deviation, again, is the distance that a data value is from the mean. Deviation, just like differing from normal, if you consider the mean to be normal. Now, the issue here that we run into is that if we do try to average these things in a kind of classic way, where by adding them up, all those deviations and dividing by, well, however many there are, you're going to end up with zero, because some of those values will be a certain distance positive, some of the values will be a certain distance negative. If you combine by addition all of those deviations, from the mean, they will add up to zero, so then they average up to zero. So that's a little bit rough as far as getting an average of these deviations, because the average of zero is zero. Okay, so how do we fix this? We're going to really kind of do a step process. So the first step isn't to go directly to standard deviation, it's to go to variance. And variance is in squared units, because squaring, whether it be positive or negative, will give you positive outcomes. So any of those deviations that are negative will square to positive, and then the averaging becomes a little easier. All right, so variance is found by adding the squared deviations and kind of averaging them. It's a little different from what you might expect. So here is a deviation. Your value minus the mean will be a deviation. Then you square it so it can't be negative. The E, remember, that means add them up. And then you adjust by averaging, but you don't average by n, you actually average by n minus 1. This is a term that's called degrees of freedom. We'll get to that. Now, the issue with variance is that if you're trying to communicate spread along with like x bar, the sample average, then you've got x bar that's in regular units, but you have your measure of spread, or variance in this case, is in squared units. So you've got a mixed metric, and you can get a big exaggeration of the differences. Now, you get an occasional person that says, well, why don't we just add up the absolute value of the deviations? And really, that's kind of not a bad idea, except that people decided at some point that by squaring them, you can find, smaller differences between deviations than you might if you just dealt with it on the basis of absolute value. At least that's what I've read. So anyway, whoops, that popped ahead. Oh, that popped back. All right, so here we're back. So we're going to get an exaggeration of the spreads, and it does help us to distinguish values which are close. Okay, variance is large if your observations are widely spread about the mean, and it'll be otherwise small if they're all close. Again, variance has a different metric than the original observations. We want some measure of spread that's in the same metric, and so we'll accomplish that by converting variance into standard deviation, because that's in the same metric, and it makes more sense to somebody you're trying to communicate if you are in the same metric with your mean and standard and spread rather, as you were in the original data. So the easy fix is to take your variance and take the square root of it. Bingo! Now you're in the same units as the original data. So that was quick. Okay, this business of n minus 1 instead of n. We are going to run into this, this notion of degrees of freedom all throughout the course. And it's used when we're dealing with samples. It addresses sampling variability, all right? It's kind of a very abstract idea. When you have small data sets, they tend to have a lot of error. So if you get an average from a small data set, it'll be less accurate than if you have a large data set. So n minus 1 is a way to try to correct for that error. And if you think about it, if you have n, getting bigger and bigger, and n in the n minus 1 getting bigger and bigger, at a certain point, your n and your n minus 1 are just about the same number. So all that's saying is a bigger sample size is more accurate. All right. So again, if you're not getting all of that, it's an interesting concept. I don't need for you to describe what degrees of freedom mean. You just have to be able to use them. So degrees of freedom measure the amount of information available for estimating variability. If we sample from a single observation, we don't have much information about what kind of numbers might be in the population because you don't have any variation there. So it's almost like that first observation doesn't count. But as soon as you get to 2 to 3 to 4 to 5 to 6, then you start, zeroing in the bigger that your sample size is, to what the actual values you're trying to estimate in a population. So that's all I'm going to say about that. And just remember that that's what you use. You don't adjust by n to average, you adjust by n minus 1. Now, this is probably one of those things I mentioned early on in the course, but the big thing about statistics is how to deal with variation. Spread. It's an important concept in statistics insofar as it is error. It is missing the mark. It is the kind of thing that we have to deal with estimation, and we have to make some kind of sense out of it in order to trust the numbers that we're dealing with. So measures of spread help us talk about what we don't know. And when data values are tightly clustered around the center of the distribution, your standard deviation, and by the way, your IQR will be small. And on the other hand, if you get a big scatter, those two measures will be large. So remember SOX, shape, odd characteristics, center, and spread. I think we're all good with all of those things now. So we report the shape, the center. We report whether things are skewed or not. If we have something nice and symmetric, we're good to go with mean and standard deviation. But if it's skewed, we need median and IQR. We talked about that. You can throw in median and IQR with a symmetric distribution too. But it's a little problematic to use mean and standard deviation with something skewed, although people do it. All right, so a few things to consider. Remember, we've been talking about mean and median, but not so much about modes. And my usual statement about modes is, what good are they? You could have more than one. Well, what if you do have more than one? You may be dealing with combined groups, like men and women combined, or small dogs, medium-sized dogs, big dogs, or horses and cattle. You may just have groups that are distinct, between towards each other. And so you'll see that in multiple modes. You might consider separating this data into groups of more like individuals. All right, if you have any clear outliers and you use the mean and standard deviation, it might be a good idea to report them with the outliers present and with the outliers removed. You're going to see different things because both of those measures, the mean and the standard deviation, are not resistant. So if you take out outliers, they're going to change. Again, your median and IQR are not likely to be affected by the outliers because of the resistance of the measures. Yeah, so keep in mind that that might be a better option. And by the way, I don't have you doing all of this, you know, getting number summaries with outliers, getting number summaries without. That just doesn't really show up in the course, but in a professional setting, you might consider doing that. Okay, so here's an example of how you would get standard deviation by hand. Here are your observations. All right, there's 6 of them, I believe. And let's see, 1, 2, 3, 4, 5. Check that. There's 7. If we calculate the mean, we're going to get 1,600. And if you subtract the mean from all of these individual observations, you are going to get all the deviations. That's your x's minus x bar. X sub I means like that little subscript I could mean that's x1, x2, x3, x4, just so you can tell which data point is which. But the point is that these total 0. So averaging them isn't going to give you any kind of, you know, meaningful spread. So again, we square, and now we've got everything positive, and we have a great big number here. So we're into a different metric. Squared units typically are bigger. So then we add them all up and divide by n minus 1, and that will give us our variance. All right, so there's your sum of your squared deviations, and you're adjusting by dividing by 6 as opposed to 7. Remember, n minus 1. And so that number is your variance. That's pretty big. It's out of the league of your original data values because those are in squared units and your original data isn't. So you fix it to take that square off the s, and now you've got something a little more digestible, don't you think? So 189.24. So your limitations, don't mix up IQR with mean. IQR connects to median, standard deviation connects to mean. You use the mean to get your deviation. So the standard deviation is built with the mean, so it must be joined together with the mean, not with the median. You can have a standard deviation equal to 0, which is no spread, and that occurs when all your observations are the same. Otherwise, your standard deviation has to be above 0. There are no negative standard deviations. Of course, your standard deviation gets larger when your spread does, and it is strongly affected by extreme observations, so it is non-resistant. Throw in a weird value, throw in a lot more spread, average it in, just like with the mean, things could go a little haywire. So here is the assignment, and what I want to do is just show you how you could actually go ahead and calculate standard deviation by hand. Using the TI Nspire calculator, which I've got here. All right, so let's just say you're starting from scratch and you don't know anything about this. So what I'm going to do is first calculate the mean. I don't need to sort it. So I'm going to add a calculator page. Check that. Let me go home. Let me escape out of here and go home. So add a calculator page. And what I'm going to do is find the mean through a 1var stats. So remember what it is. You press your menu and statistics and stat calc and one variable stats. One list, and that's going to be observations. I don't even know what this data is from, but let's go with observations. All right, so the ridiculous thing is that we've got the standard deviation right here, and it agrees to what we saw in the PowerPoint, but I'm looking for the mean, and the mean is 1600. So I'm going to go back to this, and I'm just going to go ahead and I'm going to find all of my deviations. So let's label this deviations, and let's give this a formula. That'll be, let's see, this will equal, let's find the equal sign, I guess it's here, OBS minus 1600. And let's hope that works. So hit enter. Okay, there they are. There they are. And you know what? Let's check to see if they actually do add up to 0. Why not? So I'm going to go back to here, and I'm just going to type in, there's a command that you have. It's sum, and you can get it out of the little book here and find it. And I'm just going to say sum up OBS. Enter. Oh, that should have added up to 0. Hold on and let me check and see what I did here. Just a second. All right, idiot me. We don't need to sum up the observations. We need to sum up the deviations. I don't know. I just had a little bit of a brain issue here. So let me just go ahead and put that in there. See how it went black? So it is an actual variable. I should have caught that. So let's hit enter. And they do add up to 0. So to average those things would be pretty useless. So let's go ahead and square those. And let's just call those S deviations. And let's say that that equals, let's hit the equal sign. That equals DEV. And let's go ahead and put a square on it. And let's go ahead and hit enter. And so there are your squared deviations. All right. So let's go ahead and add those up and then average them. And we should get variance. And then we can take the square root of the variance. So let's go back to your page here. And let's go ahead and do sum. And that would be SDEV. All right. And so we'll hit enter. And remember that number? It was in the PowerPoint. So we can then just go ahead and hit divided by. And we had 7 observations, so we have to adjust that by 6. So we'll divide by 6. Oh, I hate it when it does that. All right, let's go ahead, and I always forget that it's going to give you a fraction. So let's divide it by 6.0. All right, no problem. Now we got it. That's actually your variance right there. So to get standard deviation, I'm going to go ahead and divide that. So 35811.7, and we're going to take the square root of that. So hit enter. And remember that number? So now you know the whole thing is legit. So I just wanted to show you that the process does work. It's tedious. I much prefer the 1 var stats, and it just pops right up and you don't have to worry about it. So I'm going to call a halt to this and get you on your way. Hope you have a great weekend, and we'll get together next week.